We are solving question 34 of 2012 GATE Chem 100. The insulated wire is exposed to air at 30 degrees Celsius. The convective heat transfer between the wire and the surrounding air is characterized by the heat transfer coefficient of 10 watt per meter square Kelvin. The temperature at the interface between the wire and insulation is. So, in this question, we have been given a long wire whose length is 5 meter and diameter is 2 mm. So let's just consider this as the wire where diameter is 2 mm, that is 2 into 10 raised to minus 3 meter. Length we have been given as 5 meter, and this wire is wrapped with an insulation of thickness 1 mm. So let's consider this as an insulation, and the thickness we have been given as 1 mm. That is, we can write this inner diameter DIS 2 mm, and outer diameter will become E0 as 4 mm. The insulated wire is exposed to air at 30 degrees Celsius. That is, the outer temperature is 30 degrees Celsius. And then we have been given this thermal conductivity. The wire is 0.1 watt per meter. The insulation is 0.1 watt per meter Kelvin. And the heat transfer coefficient H is 10 watt per meter square Kelvin. And we have to find the temperature at the interface between the wire and the insulation. So here, that is, here we have to find this temperature Ts at the surface of the wire. Now, let's draw the resistance diagram. So if Ti is the temperature of the wire, and the temperature of the wire will remain uniform, so it will be the same at the surface. So let's just call it as Ts. So throughout the wire, the temperature will be Ts, and then we have the insulation, and due to insulation, we will be having a conductive resistance. That is R1. Then we'll be having the convective resistance, that is R2. And the outer temperature we have been given as 30 degrees Celsius. Now the overall heat balance, we can write it as Q is equal to Ts minus 30 upon R1 plus R2. Now R1 we can write it as R0 minus Ri upon K times log mean area, and ALM, that is a log mean area for the cylinder, we can write it as A0 minus AI upon ln of A0 upon AI. So area we can replace it as 2 pi RL for outer it will be 2 pi r naught L, and for inner it will become 2 pi r I L. So, and we can cancel this 2 pi r 2 pi L, and in terms of radius we will be uh, in terms of radius we can write this as 2 pi L. So we have taken this 2 pi L as common, r naught minus Ri upon ln of r naught by Ri. Now we can put this value of ALM over here, and we can get the radius as r naught minus Ri upon k times of r naught minus Ri upon ln of r naught upon Ri. And we also have this 2 pi L. This r naught minus Ri will get cancelled out, and the r1 we will be having as ln of r naught upon Ri upon 2 pi kl. That is the conductive resistance within cylinder. You can straight away remember this formula. Now R2. So let's just calculate the numerical value of this term also. So R1 will be ln of R0. The outer radius is 4 by 2. It will become 2 mm, and the inner radius will be 2 by 1, that is 1 mm, on 2 into pi is 3.14. The value of K thermal conductivity we have been given as 0.1 into length is 5 meter. So you can solve this and you will get the value of 12207. It is R1. The conductive resistance is 0.2207. Similarly, the convective resistance R2, we can calculate it as R2 is equal to 1 upon H naught into A naught, where in H naught we have the value as 10. The outer surface area is 2 pi R naught L, that is we can write it as 2 into 3.14. The outer radius is 2 mm, 2 into 10 raised to minus 3 into length of 5 meter. And you can solve this, and the final value of this outer radius will be 1.592. So we have this resistance R1 and R2, and now we will be putting into this heat balance equation, that is Q is equal to T, temperature at surface, minus 30 upon R1 plus R2, and Q we have been given as 100 watt. So 100 is equal to Ts minus 30 upon R1 we had 0.2207 plus R2 we have 1.592. So from this we can get the answer as Ts upon 30 upon 1.8127. You can solve this for Ts, and you will get the temperature at the surface as 211.27 degrees Celsius. So the final answer is 211.2 degrees Celsius. That is option A. We are solving question 35 of GATE 2012 Chemical Engineering paper. The question is, in a counterflow double pipe heat exchanger, oil is cooled from 90 to 40 degrees Celsius by water, which enters the inner tube at 10 degrees Celsius. The radius of the inner tube is 3 cm and its length is 5 meter. Neglecting the wall resistance, the overall heat transfer coefficient based on the inner radius in kilowatt per meter square Kelvin is dash. And we have been given the mass flow rate and heat capacity of both the oil and water. Now, here we have been given a double pipe heat exchanger, and we are having the counter flow. So let's just consider oil enters the tube side from here, and the inlet temperature is 90 degrees Celsius and the outlet temperature we have been given as 40 degrees Celsius. Mass flow rate is 2 kg per second and Cp is 2.1. This will be the flow direction, and the water will enter in the opposite direction in the outer tube, and the inlet temperature we have been given as 10 degrees Celsius. Outlet temperature, T out water we haven't been given, and we have been given mass flow rate as 1, CPS 4.2. Now if we draw the temperature profile along the length of this double pipe heat exchanger, we can draw it as, for this oil, temperature decreases from 90 to 40 in this direction. Similarly for water, the temperature will rise from 10 degrees Celsius to some value, that is T naught of water, T output of water. Now the energy exchange between this hot fluid, that is oil and the water, we can equate to find this outlet temperature of the water. That is, we can write delta Q of water is equal to delta Q of oil, that is m dot Cp is equal to m dot Cp delta T. This is for oil and this is for water. For water we have been given the mass flow rate as 1, Cp we have been given as 4.2, delta T will be T outlet minus inner temperature, inside temperature was 10 degree. Similarly for oil we can write it as 1 into 2 into 2.1 into temperature difference, in this case is 50, that is 90 minus 40. That is, we can write this as T minus 10 is equal to 50, and this T outlet of our water will be 50 plus 10, that is 60 degrees Celsius. So here this is 60 degrees Celsius and inlet was 10. So at the exit of the heat exchanger, the temperature difference is delta T2 is equal to 40 minus 10, it will become 30 degrees Celsius. And at the inlet, it will become delta T1 is equal to 90 minus 60, that is 30 degrees Celsius. Now, usually we will be using this log mean temperature difference to calculate the temperature difference due to which this heat exchange occurs. But in this case, since delta T1 is equal to delta T2, the log mean temperature difference we can write it as either delta T1 or delta T2. So that is equal to 30 degrees Celsius. So this we can use to calculate the overall heat transfer coefficient based on the inner radius. So that is, we can write Q is equal to Hi Ai into delta T is equal to M Cp delta T. Now this should be log mean temperature difference, but for our case this will be 30 degrees Celsius. So this we can consider either for oil or for water, whatever we want. So let's just consider this for oil. That is, we can write HI is equal to area will be 2 pi RL, that is 2 into pi to the radius of the pipe we have in inner tube is 33 centimeter, that is 3 into 10 raised to minus 2 meter, into length we have been given as 5 meter. 5 into delta T will be 30 degrees Celsius from the earlier slide. Mass flow rate of the oil was 2, Cp was 2.1, and delta T was 90 minus 40, that is 50 degrees Celsius. So from here we can get this HIS 210 upon that is, you can write 6 pi 10 raised to minus 2 into 150. So you can equate this and we will get the value of HIS 7.43. The units will be kilowatt per meter square Kelvin. So the final answer from the given options, we will select it as 7.43 kilowatt per meter square Kelvin, that is option B. We are solving question 45 of GATE 2012 chemical engineering paper. The question is, in a 1-1 pass floating head type saline tube heat exchanger, the tubes with outer diameter 25 mm and inner diameter 21 mm are arranged in a square pitch. The tube pitch is 32 mm. The thermal conductivity of the shell side fluid is 0.19 watt per meter Kelvin and the Nusselt's number is 200. The shell side heat transfer coefficient in watt per meter square Kelvin rounded off to the nearest integer is given by the which of the following option is correct. So for the shell into heat exchanger, we have to find the shell side heat transfer coefficient. Now here in this question, we have been given that the tubes are arranged in a square pitch. That is, they will be arranged in this fashion, and the tube pitch we have been given as 32 mm. That is, let's just call it as PT is equal to 32 mm. Tube pitch is the distance between the center of this tubes. So that is, this distance will be PT. Now, and we have been given the thermal conductivity of the shell side fluid, that is K is equal to 0.19. Nusselt's number we have been given as 200. And we have to find the shell side heat transfer coefficient. Now, Nusselt's number, we define it as H D upon K, where D we call it as the equivalent diameter. So this equivalent diameter is defined as 4 times of flow area upon wetted perimeter. And this will become 4A upon P. Now we need to calculate this flow area and wetted perimeter. From this we will be having the equivalent diameter, and we already have the values of Nusselt's number and thermal conductivity. Using that we can calculate the shell side heat transfer coefficient. Now the flow area, A will be the area through which the fluid is passing if we consider this square whose one side is PT. So, and this entire thing will be flow area. So this part. So we can calculate the area of this inner side through which the fluid is flowing in the shell side tube as. So we can calculate the area of square PT square, and we can subtract these individual areas, that is 1, 2, 3 and 4. So PT square minus of 4 times of the area of this individual section of this circle. So it will become 1 by 4 into pi. The area of the circle is pi d square by 4. It will become this. That is, the area will become PT square minus of pi d square upon 4. Now the perimeter, we know that perimeter will be 2 pi r, that is pi d naught. Here also that diameter will be the outer diameter. Now we can write this equivalent diameter as D is equal to 4 times area we calculated as PT square minus pi d square by 4 upon pi d. Okay, so now we can replace all these values. 4 into 32 square minus of pi into outer diameter is 25 mm upon 4 upon pi is 3.14 into 25. So this we can write as 4 into 1024 minus of 490 upon 3.14 into 25. So this we can solve, and we will be getting the value of this diameter as 27.15 mm. Now once we have this diameter, we can use this Nusselt's number formula. This Nusselt's number is equal to H d upon K. We have to find the shell side heat transfer coefficient. So this will become H is equal to Nusselt's number into K upon D. And the Nusselt's number we have been given as 200 into thermal conductivity. It is 0.19. And the diameter we found out as 27.15 mm. We can change it into meter. The final heat transfer coefficient by this calculation will be somewhere around 1399. And from the given options we can select the value closest that is 1400 rounded off to the nearest integer. So the shell side heat transfer coefficient for the shell and tube heat exchanger is 1400 watt per meter square Kelvin.